So what I want to look at here is I want to look at something called infinite series. So we've been looking at geometric sequences, arithmetic sequences, and different sequences. And now we're going to look at series, which are summations of sequences. All right. So we'll start out with a definition. And so our definition here is that an infinite series is an expression of the form of the sum, and that's what this sigma means. Okay, the sum of n equals 1 up to infinity of a of n, where an is some sequence. Okay, a1 plus a2 plus a3 for each positive integer k, and this is what's called a partial sum. We get sk is going to equal the first k terms of that sequence added together. Okay, and that's called the kth partial sum of the infinite series, and they're going to actually be very important for us as we start looking at finding the values for these series. And if the sequence of partial sums converges to some real number s, the infinite series converges. If we can describe the convergence of a series to s, we call s the sum of the series, and we write the sum n equals 1 up to infinity, a sub n equal to s. Okay? And if the sequence of partial sums diverges, we have the divergence of a series. Okay? We have the divergence of a series. All right? So one of the key things that we're going to be looking to do here inside of this particular section is we're going to be looking at how do we write series given a particular sequence and its summation, and then secondly, how do we determine whether or not that series converges or whether or not it diverges, which is going to be a major question throughout the remainder of the next two chapters. Let's take a look at an example. Let's say, for example, we have let 1 over 1 times 2. Okay, let's have this be our series. 1 over 1 times 2 plus 1 over 2 times 3, all the way up through 1 over 119 times 120. And let's write the series in sigma notation. So this is one of those things that you should be able to do. Given a sequence, we should be able to then write a summation for it. Okay, so we'll have A1 is going to equal 1 over 1 times 2. And then A2 is 1 over 2 times 3. And so one of the things that I'm going to notice is that A sub n is going to end up equaling 1 over, and so notice that's a 2, that's n, right? Okay, so n times, and then this one here is n plus 1. The second term is n plus 1. So it'll be the sum of 1 over n times n plus 1. So we'll now get, okay, the sum n equals 1 up to, and now in this case we need to figure out what we're going to go till. Notice that we're going to go up to 119 because n will be 119 and then n plus 1 is going to be 120. So we'll get n equals 1 up to 119, okay, and this will now be 1 over n times n plus 1. Now let's ask ourselves the question, what about the infinite series based upon this series? Does, in this case, the sum I equals 1 up to infinity of 1 over I times I plus 1. Okay, so that's our series. Does it some value? It's a good question. Okay, and we're gonna figure out have to figure out what the answer to that particular question is. So what I'm gonna do in order to answer that question, I'm gonna have the sum I equals 1 up to infinity of 1 over I times I plus 1 equals the sum I equals 1 up to infinity of 1 over I minus 1 over I plus 1 if we use a partial fraction decomposition. Okay, so that's another place where partial fractions might actually come in kind of handy, is in solving these kind of things. Look at the partial sums and we'll map that out. So I'm going to get 1, like if I let I equal 1, this is going to be 1 over 1 minus 1 over 1 plus 1. All right, that's the first one. Okay, plus, right, 1 over 2 plus, and this will be 1 over, or minus 1 over 3. And then plus 1 over 3 minus 1 over 4 plus 1 over 4 minus 1 over 5. And we're going to keep doing this. And what we want to notice is that these middle terms, okay, they're all going to go away. And so eventually what we'll have, if we look at the kth partial sum, we're going to end up with 1 over 1, and then this thing here, That's k plus 1, isn't it? Okay, so we got 1 over 1 minus 1 over k plus 1. So what we get is that this implies that the sum I equals 1 up to infinity of 1 over I minus 1 over I plus 1, okay, is going to equal, or excuse me, that the partial sum, 1 up to n, will equal 1 over, or excuse me, 1 minus 1 over n plus 1. So this is actually our partial sum. Right? That's the partial sum. And the partial sum will end up giving me 1 over, or 1 minus 1 over n plus 1. Now what I want to do is what happens as we take n to infinity, right? Because that's going to tell me whether or not I have convergence. Right? So I found out, here's my partial sum. So now I take the limit as n goes to infinity of 1 minus 1 over n plus 1. Okay, that partial sum. And what is that going to equal? That's going to end up equaling 1. Since what we just found, the sum, I equals 1 up to infinity of 1 over I times I plus 1 equals 1, the series converges. We actually found a limit to that, right? The series converges. It exists. It converges. All right? So that's going to be kind of some of the things that we're going to end up doing inside of this section is we're going to, go out, find ourselves a series, and then we're going to make some distinctions about whether or not that series converges. Now, in this case, we utilize some algebra. In other cases, we're going to use some theorems in order to make some determinations as to whether or not series converge or not. So let's take a look at two very useful series. The first one is called the Harmonic Series, and it's going to be the sum n equals 1 up to infinity of 1 over n, and that'll equal 1 plus 1 half plus 1/3, right? All the way up through infinity, okay? And the thing about the harmonic series that's going to end up being very important is that the harmonic series is in fact divergent. Even though it diverges very slowly, it is actually in fact divergent. All right, so that's the first one. And the second one that we're going to look at is this geometric series. So a geometric series is a series of the form n equals 1 up to infinity a times r to the n minus 1, where the values inside of the series, like that sequence, is in fact a geometric sequence. Okay? It's a geometric sequence, and we're going to have some rules for whether or not this series in fact converges. If, say, for example, the absolute value of r is less than 1, the series will converge. And if absolute value of r, and we get this value, this is actually going to give me the value for the actual series, right? It'll be a over 1 minus r. And if the absolute value of r is greater than or equal to 1, the series is going to diverge. So what we're going to do with this is we're going to do a little bit of proving work, okay? We'll start out with what if r equals 1? And we're going to show that, in fact, the series diverges. So let's let r equal 1. And let's consider the partial sums. Okay, so we're going to take the sum I equals 1 up to n of I equals 1 up to n, of a r to the I minus 1. And that's just going to end up equaling, right, because r equals 1, it's going to be I equals 1 up to n of a. And that's going to end up equaling a plus a plus a. And we're going to do that n times, right? So there's n of them. So that's going to equal n times a. So that's my partial sum. Now, to find the infinite sum, I'm going to take the limit, or I'm going to say I equals 1 up to infinity, okay, of a r to the I minus 1 is going to equal the limit as n goes to infinity of na, which is equal to infinity. Right? So the series diverges. That is not an actual number, that is infinity, so the series is going to diverge. That's what that means. That means divergence. So the series diverges. So let's consider, let's let r not equal 1. Then we'll look at the partial sums, and Sn is going to end up equaling a plus ar plus ar squared plus ar, and then this will all go up to ar to the n minus 1, right? So we don't quite have all the way up to AR to the n, but just AR to the n minus 1, okay? Right? Because that's the last term. I is n, so to the n minus 1. Then we're going to consider r times s to the n. So now we'll multiply everything by r, and we get AR plus AR squared plus AR cubed plus, and then we're going to go all the way up to AR to the n. So what we get here is we're going to actually now subtract those two. We're going to take Sn minus Rsn. And so that's going to end up being, well, it'll be A, right? Because we're going to, all these terms are going to go away. Even all the way up to the AR to the n minus 1. And what we're going to be left with is the AR to the n from Rs to the n and A. So this will be A minus AR to the n. Okay, and that's our partial sum. Well, what does that mean? Okay, so let's actually, we're going to pull out, we're going to get Sn is going to now be equal to, or Sn times 1 minus R is going to equal A minus A to the AR to the n minus, A minus A times R to the n. So that means that my partial sum is going to equal A minus AR to the n over 1 minus R. Okay? Now, let's consider if R, or the absolute value of R, we'll consider if the absolute value of R is less than 1. So basically, R is greater than negative 1 and less than 1. Okay, what happens there? What occurs at that time? Okay? Well, let's consider now our Sn. And I'm going to rewrite that as A times 1 minus R to the n over 1 minus R. And let's consider the limit as n goes to infinity of A times 1 minus R to the n over 1 minus R. Well, R to the n is going to go to 0 because the value for R is less than 1. So R to the n goes to 0 as n goes to infinity. But what we're left with is we're left with everything else. Everything else is just simply constant. So that limit as n goes to infinity is going to just end up equaling A over 1 minus R. Okay? And that's what happens if the absolute value of R is less than 1. What about if the absolute value of R is... So let's suppose the absolute value of R is greater than 1. Okay? So now when we take the limit as n goes to infinity of A times 1 minus R to the n over 1 minus R, what we're going to get is that this term, right, this term goes to negative infinity. So the part on the top is going to go to negative infinity, okay? Part on the bottom is going to be negative as well. So this is actually going to end up being equal to infinity, right? So if absolute value of R is greater than 1, the series diverges. And we're going to use that in order to help us understand when do series diverge and when do they converge, all right? So that fact, the fact that we just actually went in and proved, we're going to utilize in order to actually go in and prove if a series diverges or converges. Okay, it's going to be a very helpful little tool. So let's go back up, see what the theorem says again. So we have a geometric series with a constant ratio of R. If that constant ratio is less than 1, the series is going to converge. And we're in fact going to get the value for the series. If on the other hand, the absolute value of R, the common ratio, is greater than or equal to 1, then this series is going to diverge. Let's take a look at an example. All right, so let's take a look. Does this series 1 minus 1/5 plus 1/25 minus 1 over 125 converge or diverge? Okay, so we'll start out, and what we want to do is we want to figure out what exactly is the sequence that we've got going on behind the series. So we'll look at A1 is going to equal 1 over, and 1 over 1, okay? And that actually is 1 over 5 to the 0th power, okay? That's going to be kind of handy. A2 is going to equal 1 over 5, and that's 1 over 5 to the 1. A3 is going to equal 1 over 5 squared, and that's 1 over 5, or 1 over 25, right, which is 1 over 5 squared. And we can kind of see that that's what's happening. Now, if I rewrite this, this is going to end up equaling 1 over 5 to the 1 minus 0, 1 minus 1, excuse me, 1 minus 1. 1 over 5 to the 1 is going to be 1 over 5 to the 2 minus 1. And 1 over 5 squared is going to be 1 over 5 to the 3 minus 1. All right? But then I have this added little wrinkle because actually this isn't 1/5. It's actually negative 1/5. So we're going to go back and forth between positive and negative. So the first term is going to be positive. So what I'm going to do is I'm going to take this is going to be negative 1. And since it's positive, since the first term is positive, I'm going to actually have it be negative 1, okay, to the 1 plus 1, so 1 squared, times 1 over 5 to the 1 minus 1. And that's essentially how we're going to write this, okay? And then we'll have negative 1 to the 2 plus 1 times 1 over 5 to the 2 minus 1. And so we can see, you know, what the pattern is now. It's now going to be negative 1 to the n plus 1, okay, times 1 over 5 to the n minus 1. All right, that's my sequence. So my series is now going to be the sum n equals 1 up to infinity of negative 1 to the n plus 1, okay, times 1 over 5 to the n minus 1. Okay? Now, let's take a look back at our conversation about geometric series. I'm going to go back and look at my theorem. So a geometric series is a series of the form, and it has a times r to the n minus 1. Oh, good. That's what I've got. We'll take a look at that in just a second. Okay? If absolute value of r is less than 1, the series is going to converge, and we'll end up with the sum is going to equal not negative a, but just a, okay, to the n minus 1 is going to equal 1 over a over 1 minus r. So I'm going to just change this around to make it look like that. So this is going to end up equaling, this will be negative 1, okay, to the n plus 1, okay, times, all right, 1 over 5 to the n minus 1. Right? I have a problem here, and then my problem here is with this n plus 1. So what I'm going to do is I'm actually going to change it. I'm going to change it to an n minus 1, and I can do that because it's going to end up giving me the same answers. So like, for example, if I change this to 1 minus 1, it's going to be negative 1 to the 0th power. Okay? So there's 0, which is fine. That'll end up being positive. And this will be 2 minus 1, which is going to be negative 1 to the 1, which is going to be negative. So it'll give me my right backwards and forwards. So let's actually do that. And we'll use that as just as a principle. Let's use the n minus 1 rather than the n plus 1. Okay? So what I'm going to do now is I'm going to move all of this together. I'm going to get the sum, right? This infinite sum, n equals 1. And I'm going to move all of this information in. I'm going to end up with this negative 1 over 5. And this is now going to be to the n minus 1, right? Because the negative 1 moves inward. The 5 moves inward, and then we're just taking it all to the n minus 1th power. Super important, right? Okay, it's going to end up becoming a kind of a crucial fact when we actually go out and determine whether or not these series converge. So this will equal then the sum, well, that's it. That's actually all of it. It's going to be n equals 1 up to infinity. Now our r is going to equal negative 1/5. And the absolute value of negative 1/5 is in fact less than 1. So the series converges. Because it's geometric. See that? That's by definition a geometric series. So the series converges. So what we end up with is my series, okay, n equals 1 up to infinity of negative 1 over 5 to the n minus 1 is going to equal a, now that's, the a is just, there's a 1 in front of this, so 1 over 1 minus a negative 1/5. So this is going to be 6/5, so this is going to end up equaling 5/6. And that is the value of my infinite sum. So just to kind of review what we did, we went in, we made a determination, right? We looked at our series, transformed it into a sequence, and we took the individual terms of that sequence, right? 1 over 1, right? And what we wanted to do here is to turn it into some powers to the n minus 1, right? And that's essentially what we did here with both the negative 1, because we were switching signs, and the positive 1/5, right? Once we did that, we could transform it into this geometric series, or it actually allowed us to transform it into a geometric series. Then I stated, okay, here's r. R is negative 1/5. I noticed that negative 1/5 in absolute value was less than 1, so that told me that the series converged. So the sum of n equals 1 up to infinity of negative 1/5 to the n minus 1 is then going to equal the value that I had inside of my original formula. And that finishes that. So let's take a look at this series. So let's ask the question, is this series convergent or divergent? And what we're going to do is we're actually going to utilize those techniques that we use from the geometric series. So what I need to do is I need to turn this series into the form, okay, the sum n equals 1 up to infinity of a times r to the n minus 1. Right, just into our geometric series form. Once I do that, I can make a determination as to whether or not the series is convergent or divergent, and I can also determine what the value is for the series. So I'm going to look at this, and I'm going to just do some algebra. So I got n equals 1 up to infinity, and 2 to the 2n, so I know that's going to be 2 squared, okay, and I'm going to make that to the n, right? So now I've actually pulled out the squared, and this 3 to the 1 minus n, I actually have a trick for this. This is actually going to be negative of n minus 1. Okay? So that's going to end up being the negative of n minus 1. Okay? So if I rewrite this now, this is going to give me the sum n equals 1 up to infinity, and this will be 2 squared, or rather 4, okay, to the n, and this will then be 3 to the negative 1, right, to the n minus 1. So we just utilize our rules of powers in order to be able to do something like that. Okay? Now, one of the other things that I want to notice is that I want to turn this needs to go into an n minus 1 term. I need to turn that into an n minus 1. And so how I'm going to do that is I'm actually going to do this. I'm going to rewrite this as the sum n equals 1 up to infinity of 4 times 4 to the n minus 1. Okay? And then this will then be times 1/3 to the n minus 1. And now I actually have all of my powers are in terms of n minus 1, which is our goal, and which is our goal when we're trying to transform this series into something where we can use the geometric series. Okay? So this is now the sum n equals 1 up to infinity of 4 times, and this will then just be 4/3 to the n minus 1, because we can just bring it in because they're all the n minus 1 term. So r is then going to equal 4 over 3. The absolute value of r is greater than 1, so the series diverges. And that's how we prove, in fact, that this series diverges utilizing the geometric series theorem. Now, a couple things to get about this. One is our goal here, if we kind of notice that what we have is just a multiplication of some different values, is to transform all of these into the form for our geometric series. Once we get it to there, then we can utilize the geometric series test in order to determine if the series converges or diverges. All right, so that kind of introduces us to series, looks at two really canonical value forms, the harmonic series, which will become really important later on, and this geometric series. And so, this should kind of help you get an understanding of what it is that we're doing when we're trying to determine if a series converges or diverges.